Hello. In this unit, we're going to talk about architectural elements of deep networks that improve the effectiveness of gradient descent, of stochastic gradient descent. We're going to talk about four architectural innovations that were important in the deep learning revolution to improve the training time and the training effectiveness of models. So the first thing I want to point out is RELUs. The RELU is the activation function used almost universally, or some form of RELU is used almost universally in modern deep networks. Originally, in linear threshold units, you would take a linear sum, a weighted linear sum of inputs to the neuron, and compare that to a threshold value. And if it was above threshold, the output would be full voltage, straight on. It was a step function activation function back in the 1940s. That got replaced by a differentiable sigmoid function. It starts at 0 and smoothly transitions to 1 and then stays at 1. So it's like a differentiable version of the step function. Then in AlexNet in 2012, dramatically increased or improved SGD performance, training time, was achieved with the rectified linear unit, the RELU. So the idea is that we take a linear combination, a weighted sum of inputs, and then that defines this X value, and then we take the max of that value and 0. So the activation function, the function that's receiving the linear combination, is 0 up until a threshold, which is always taken to be 0, and then it's linear forever. And the advantage of this is that it does not saturate. If this eventually stopped increasing, then the derivative of this with respect to the input becomes 0. And if the derivative becomes 0, there's no learning in this neuron because the gradient has to go back through the neuron to update the weights. And if the gradient is 0, the weights don't get any update. So the replacement of a step function or a sigmoid function with this rectified linear unit greatly improves the effectiveness of gradient descent, of SGD. So this was 2012. Okay, the next thing I want to talk about is why are neural networks difficult to train? And there's a fundamental phenomenon known as exploding gradients and vanishing gradients. So gradients can go to 0, like that's what would happen if we were using a sigmoid and we were saturated. The gradient would go to 0. The gradient can also explode, get so large that gradient descent takes the step that's too large and undermines its ability to converge to a particular value. So the gradients can get too small or too large, vanishing or exploding. So why does this happen? It's not just the activation function. Let's consider y, which is a linear sum of weights times an input value. So this is the weighted sum that's going into a neuron. Here's the weighted sum going into a neuron. This is the y. And consider the value of the values y we're getting for fixed values of the weights. If we're summing a large number of terms, and these weights, say, were order 1, suppose these weights were all roughly 1, and suppose all the values were roughly 1. That means this y would be a sum of values of size 1. So it would depend on how many elements we're adding. And if we're adding too many elements, then this value of y gets large. And if we repeat this across many layers, then the value of y would get larger and larger at every layer. This is the previous layer, this is the next layer. At every step of this, we're amplifying or multiplying the average value of this by taking this sum. And that if these were independent, taking a sum of independent values increases the sum by 1 over the square root of the number of things we're adding. So if we initialize the weights to be 1, we get exploding values. And once we get exploding values, we're also going to get exploding gradients. So this is a problem. Now, it's also a problem if these numbers are too small. If these numbers are smaller than 1 over square root of n, then every time we go through a layer, our values are getting smaller, and they're getting exponentially smaller as we go up through this. So as the values get smaller, that's going to cause the gradients coming the other way to also get smaller. And again, we get vanishing gradients. Okay, so this is what I just said. I tried to say it intuitively. This is saying it more explicitly. What's happening here is that if we take the gradient on the weight, right? Suppose you want to take the gradient on the weight. We have a gradient on the output y, and the gradient on the weight is the gradient on y times the value of x. So I just said, if the values of x get too large, the gradients get too large. And this equation is explaining that. It's saying the gradient on the weight is proportional to the value of x. So if the values are large, the gradients get large. If the value gets small, the gradients get small. So how do we fix this? So I said, as we go through a layer of the network, we can make the values to scale up, get too large, or we can make them scale down and get too small. And whether they go up or down depends on the values of the weights. And it turns out that you want the values of the weights to be roughly 1 over the square root of n, assuming that this sum is summing independent values. And if we make the values of the weights proportional to 1 over the square root of n, then this, and if the inputs have order 1, then the output will have order 1. You're compensating for this summation. So this is called He initialization. So the idea is that we initialize the weights. Now, when you initialize a neural network, you initialize the weights randomly, but you can control the scale or the size of those weights. And we want the scale or size of those weights adjusted such that at initialization time, at least, the values of y are not being amplified or diminished as you go through layers of the network. So in He initialization, this is the standard initialization still used. What we're going to do is we're going to initialize the weights to be Gaussian random variables. We're going to initialize them by drawing values from a Gaussian. And the important point is that the standard deviation of that Gaussian is going to be taken to be 1 over the square root of 1 over n. And that is the so-called Goldilocks value, where the values of the network remain order 1 throughout all the layers of the network. And I should also say that what this is all really about is facilitating deep networks. Gradient descent and training of neural networks is much more challenging in deep networks. So we're very concerned with these deep networks. So again, this is just the formula for He initialization. Assuming independence, what we're going to try to do is maintain an invariant across layers of the network. So as we go across layers of the network, we want all of our values, and now we're going to think of them as random values. We're going to want all of our values to be random values with mean 0 and standard deviation 1. So if we assume that this has mean 0 and standard deviation 1, and we're initializing this to have mean 0 and standard deviation 1, then this will have, mean 0 and standard deviation 1 over the square root of n, the Goldilocks value for the weight. So we're assuming this has 0 mean and unit variance. This has 0 mean and unit variance 1 over the square root of n. Then this will have 0 mean and unit variance So as we're going through the network, all of our values are supposed to have 0 mean and unit variance. Okay, now that's true at initialization. And maybe if we're lucky, it stays kind of true. But as we train, the network's changing. And those weights are changing. And we would like to guarantee this invariance that the values in the network are order 1 throughout the entire training process. So the next idea is batch normalization. And this came in later. This was after AlexNet, but still fairly early in the deep revolution. So what we're going to do is put a layer in the network that renormalizes the inputs to that layer. So here we're taking a layer, and I'm thinking of this as being a vision layer. So in a vision layer, we always have a batch index. This is saying what batch are we at? So remember, in deep learning, we typically take a batch of inputs, sometimes called a mini batch, although lately they're not so mini, they're huge. We take a batch. This is saying which batch element we're looking at. So B might be, 1 through capital B. That's the number of training examples we're considering in a batch. And if this is a vision model, then this layer might assign to each position X and Y in the image, sort of a place of a pixel, some number of feature values. This is the shape of a layer in a convolutional neural network. It takes a position in the image, and it has a bunch of feature values. And what we're going to do is we're going to take a layer that takes this input, and it's going to produce the next layer, right? It goes from this input layer to this output layer. And what it's going to do is make sure that this output layer, that the values in this output layer are normalized, meaning that we want them to have 0 mean and unit variance. So this is how this works. So I'm going to define for each feature and each position. Okay, so this is essentially saying for each neuron. So for each neuron in this network, this is a position and a particular neuron value. This is an index over the neuron value. I've been saying feature, but think of it as naming of a particular neuron. So this is the neuron. This is the place the neuron exists in the visual cortex, say. So this is the place that the neuron is in the visual map. This is the name of the neuron. I'm going to take an average over the batch. Okay, so remember, we're doing a whole batch at once. I'm taking an average over the batch of the value at that batch. So this is an average over the batch of the response of this particular neuron across that batch. And what I'm going to do is I'm going to compute a standard deviation. This is a mean. This is the mean value of the neuron across the batch. Particular neuron, its mean across the batch. I'm going to take a particular neuron and I'm going to compute its standard deviation across the batch. How much does it vary? And this is the standard formula for standard deviation. I take the square difference. I take almost the average of the square difference, but for technical reasons, you use B-1 here to make it unbiased. So I've got this neuron, one neuron. I'm computing its mean across the batch. I'm computing its standard deviation across the batch. What I do is I take the previous layer, I take each batch element, each particular batch element, I subtract the mean of the neuron over the batch, and I divide by the standard deviation of the neuron over the batch. So this is giving me something that is zero mean and unit variance according to the sample, which is the batch. So this is normalized, and it's called batch normalization. We're normalizing over the batch. Now, this batch normalization is per neuron. Okay, so it's for each neuron, for each position in the image, it's computing an average, it's computing a mean and a standard deviation. And here the neuron is really at a position in the image. But if you think about the parameters in a convolutional neural network, really in some sense, you're using the same neuron at different positions. So at different positions in the image, it's really the same neuron. The same neuron is being repeated. The computation at the different positions in the image is reusing the same weights. So you can think of it as the same neuron at different positions. So in spatial batch normalization, we're going to normalize not just over one position, but we're going to normalize over all positions. So we normalize over the batch, and we normalize also over all the XY positions of a particular neuron. So here we're thinking of the neuron as being reused at every position. So we're getting a much larger sample of values. We're getting a sample of values at each batch and at each position within each batch element. And we do the same thing, but we're just averaging over the position. And then we get something that's normalized. We compute it at a given batch in a given XY position, but we subtract the mean and the standard deviation measured across all batch elements and all positions. Okay. Many modern networks, including modern transformers, do not use batch normalization. Instead, they use just layer normalization. So here, we do not average over the batch at all. We only average over the position. So if we have a repeated neuron, a neuron that's being used repeatedly at different XY positions, we're only going to average over the positions, not the batch. And intuitively, we're doing something very similar. We're averaging over a bunch of different uses of the neuron, but all at the same batch element, all in the same image, right? If we were doing this with images. Now, this is particularly effective in transformers because the same neuron gets used many, many, many times in the same batch element, in the same piece of text. So you're getting a very large averaging. So if you don't average over the batch and you just average over the positions, that's called layer normalization. And the advantage of layer normalization is that you're working with each batch element independently. And when you work with each batch element independently, it's easy to run this at test time on a single batch element. In batch normalization, you've got an issue at test time application because you only have one example. You can't average over a batch. So there's some tricks people use. They compute a mean and variance that they use at test time. Layer normalization does not have that problem. It's treating each batch element independently, and therefore there's no problem at test time. You just treat that one test element independently. All right, now there's something strange about all these normalization layers. And what's strange about it is I said the point was to make the values well behaved, to make the values not get too large or too small. So In spite of that, what they do is they add an affine layer after the normalization. So the affine layer is taking each neuron and it's scaling in each use of that neuron by a scale factor gamma, scaling it up or scaling it down, and it's adding a bias term for that neuron. So it's adding back a scaling and a bias at every neuron. So it just, the normalization layer got rid of those. It made everything scale 1 and bias 0. But after doing that, we add the scale factor and the bias back, and this could even just undo the normalization. But the point here is that the input to this is now normalized. So as the network is learning, the input to this transformation is being held zero mean and unit variance. And this seems to work fairly well. In the original batch normalization paper, they justified batch normalization as saying that they're compensating for internal covariate shift. Intuitively, they're saying that as the network is learning, it's changing, the network's changing. As the network below a layer changes, it's changing the meaning or the distribution of the inputs to the next layer. In statistical terms, when the distribution over the input features change, that's called a covariate shift. So batch normalization is justified in terms of covariate shift. Someone told me that very recently that analysis of normalization has been challenged. However, modern networks do normalize. Normalization is used in all modern networks. Okay, here's the next big innovation: residual connections. So residual connections were a big innovation and are universal in all modern neural networks, just like normalization, just like RELU. So what is a residual connection? I'm going to draw this with sort of opposite. So the idea is the input is at the top and the output is at the bottom. So this is a very abstract representation of a residual network, of a residual connection. So here's an input layer, or maybe even somewhere in the middle of the network. We've got information flowing, a tensor, some tensor flowing down here in a convolutional neural network. This is, let's say, another convolution layer. It's something that's processing the information. It's taking this input and it's producing an output. And for now, I'm going to assume that the input and output are tensors of the same shape. They have the same indices. For example, if this was a 64 by 64 image with 156 neuron values at each position, if that was this shape, that's also this shape. This shape and this shape are the same. And I can take those tensors and I can just add them. So I'm adding every element. Tensor is like a giant array with multiple indices. I'm just taking each array element and adding the two values of the two array elements. And I do that repeatedly. So this appeared early in a paper by Schmidhuber's group. It was called Highway Networks. But it really took off with K-Ming He's introduction of residual networks, and he called them residual connections. Why? Why is this such a good idea? And why has it taken over and is universal in all modern architectures? The reason has to do with gradients. At the bottom of this, there's a loss function, like, log loss in predicting the next word. I should say that this is used in transformers. In transformers, this is called the residual pathway. So in transformers, you've got a loss function, which is your accuracy in predicting the next word. In images classification, you would have a loss function, which is how accurately are you predicting the class label for this image. Anyway, there's a loss function. And we're computing the gradient back from the loss function. In back propagation, we go back from the loss function, computing gradients with respect to all of our program values. These are all program values in our feed-forward network. Now, if I didn't have these residual connections, I would be back propagating into this unit and then back propagating directly into this unit and so on. If I have the residual connections, the back propagation has a path that bypasses this network. So there's a direct gradient path from here to here. And if this is just a stack of residual connections, there's a direct gradient path from the loss function back to the very first layer of the network. And that direct gradient path from the loss function to the first layer of the network allows the input layer of the network to be trained. Otherwise, the gradients get completely garbled by everything that's being done in the deep network between this loss function and the input. So that's the idea. This is improving gradient descent by providing a direct gradient path to every layer in the network simultaneously. So this is just the equations for residual connections. This is the equations for a convolutional layer. And the fundamentally, so this is an input layer to a, this is an input layer in a convolutional neural network. It says we're going to take that input layer in the convolutional neural network and we're going to do a convolution. These are just the parameters of the convolution. Just the point is we're taking this, passing it through a convolution layer to define the next layer. You can ignore the details of this or work them out if you really want to. These are just the parameters of the convolution layer. We're taking this in, this layer in, and getting this layer out of the convolution layer. And then I'm calling this a tilde because the next layer is just the sum of the input layer and the computed layer. Okay, so it's really just this picture we had before. This is just writing it in equations for the case of convolution. And just to say what I said before, this equation assumes that the shape of this tensor coming out of the convolution, coming out of this computation, is the same as the shape of the tensor coming down here. In ResNet, in the original paper that introduced residual connections, they would skip over a couple layers at the same time. So this is just a picture of skipping over a couple layers at the same time. Now, another thing you have in convolutional networks for vision is that eventually you reduce the spatial dimensions. You do a couple levels of processing at the original input image dimensions, and then you typically reduce by a factor of 2 to get, if you've got 128 by 128, you go to 64 by 64. Now, when you do that, you've got different shapes. This is, you've got something coming in that's 128 by 128 and something that's being produced here that's 64 by 64. And the way that works is you just, you take this thing, which is smaller dimension. So now these X and Y are ranging over fewer places than the input X and Y. So if you remember, we reduced the dimension simply by taking the output indices and multiplying them by a scale, typically 2. So as you walk around in the output image, you're walking around taking bigger steps in the input image. So you're covering all of the input image. And you also typically increase the number of neurons at every position. When you reduce scale, you increase the number of neurons. So what we're going to do to increase the number of neurons is simply take this tensor and pad it with 0 at the newly introduced neurons. So you get more neurons just by padding out with zeros, more places in the tensor and initializing them to 0. So here's a picture of ResNet 32. So here's an input image. And each little box here is a convolution layer, and each arrow here is a residual pathway. So you're taking the input, doing 2 convolutions, and then adding that to the input. And each one of these is adding, is doing some processing and doing some adding. It's sort of it's drawn differently from the way I drew it before. The direct path is the path that's going around the processing. This is a dotted line. That's where the spatial dimensions are being reduced. And eventually we get much smaller images, and this is ResNet 32. Now, deeper versions use a bottleneck layer, and I should have drawn a picture of this. But the idea is, in a bottleneck layer, we have images of a certain size. So we have some image of XY. This N, this is the batch index. This N is naming the neuron. So we're going to have neurons. So I've got a layer that's coming up. What I'm going to do is at each position in the image, we have a set of neuron values that define a vector. At each position independently, we're going to reduce the number of neurons. So at each position, we're going to go from saying 256 neurons down to some much fairly smaller number of neurons, like 64. So at each position, we're taking 256 neurons down to 64. Then, when we have images, same spatial dimensions, but only 64 neurons at each position, we're going to do a convolution. In Kaiming He's paper work, all the convolutions were 3 by 3. And in modern networks, they're only 3 by 3 convolutions. There are lots of reasons for that. The big reason is we're going deeper. Since we've got a lot more depth, we can get away with simpler convolutions. So anyway, all convolutions are 3 by 3. So we've got an image. We've got a large number of neurons at every position. At each position independently, we reduce the number of neurons. How do we reduce the number of neurons? We do it with a fully connected layer. So so here's our input L. This is a fully connected layer. What it means to be a fully connected layer, you can do it with a convolution, a 1 by 1 convolution. A 1 by 1 convolution just takes every position independently because it's a 1 by 1 convolution. So this is a fully connected neural network at every position in the image. And that's what that 1, 1 means. It means that kernel is looking at each position independently. And what it's doing is it's taking, this is the number of neurons in the input, and it's reducing it to the number of neurons in the bottleneck, in what's called the bottleneck layer. So this reduces N to a smaller dimension. This takes that and does a 3 by 3 convolution on it. It keeps the bottle dimension, the number of neurons in the bottle, the same. But it does a convolution. So then what we do is we take that and we expand it back to the original dimension. So here we were going from the input dimension to the bottle dimension. Here we're going from the bottle dimension back to the input dimension. So we're going back up from a small number of neurons in the bottleneck layer to a large number of neurons in the residual stream. The residual stream, the set of things we're adding together, still has the larger number of neurons. But in the computation, we reduce, convolve, expand, and then add. And this is justified by saying that this 3x3 convolution, by being done on a smaller dimension, is much faster, right? Because it's these matrices are smaller. So this ends up being more efficient computation. Now, it's worth pointing out that transformers also have a bottleneck layer, it's a bottleneck layer like this. But in transformers, the bottleneck dimension is larger. And that's a fascinating phenomenon that I was oblivious to for quite a while. And maybe we'll get back to that. Why would you have a larger bottleneck layer? But we'll get back to that later. So this is the general residual connection. We're computing the next layer Y from a layer X plus some computation. Here we're assuming Y and R of X have the same shape. Okay, so that's the end of this unit. These are 4 architectural innovations that have proven their worth, and they are universal in modern networks. So thank you very much.